Oh man, that's loud.
Yeah, don't be surprised if that's
All right. Can you hear me in the back? Great, thank you. All right, lots to cover today, so let's jump straight into it. All right, so remember this week we are focused on unsupervised learning. We've done a lot of supervised stuff so far, switching gears. Forget about the whys that you used to have. Okay, so we no longer have these like labeled or input-output pairs. Now we're just thinking about what if we get a bunch of x's? Is there anything meaningful that we can do with this anymore? We can't really do prediction, right? We can't learn predictive models because we don't know what we're predicting from what. But maybe we can still do something interesting like, try to discover some underlying structure in our data, whatever that might mean. I remember we started talking about that last time through the lens of dimensionality reduction. So trying to get these high dimensional x's and project them down into some lower dimensional space, maybe that's easier to understand, easier to work with, and so on and so forth. So today we're going to continue our discussion on that, on dimensionality reduction, and we're going to finish up principal component analysis, which we started last time, PCA. So looking through it, as it turns out, there's a whole bunch of stuff on PCA that I didn't cover. So we're gonna do some more PCA this time. There's still quite a few interesting things to tell you. Then, strictly because there's not a whole lot of time, we're only going to briefly discuss some other dimensionality reduction tools. If dimensionality reduction is sort of something that's interesting to you, let me know, and we can talk about it. Can sort of try to provide some additional resources. But due to time constraints, we're mainly going to focus on PCA, and then I'll give you a flavor of what other dimensionality reduction can look like. And then, again, we can talk about that in detail if you want. And then on Friday, we'll talk about clustering, which is a different type of unsupervised learning, also interesting. That's Friday's topic. Okay, so remember, let's go over what PCA was first, right? So PCA was dimensionality reduction. We're trying to go from d-dimensional x's to something that's k-dimensional, where k is smaller than d, right? And in particular, in PCA, we restricted ourselves to kind of what we call these linear projections, right? So some linear operation, some matrix, right, d by k, that goes from d dimensions to k dimensions. And PCA asked, what is that best linear projection that we can learn? Well, there's a whole bunch of different ways that we can define best, or just like good, like what's better than something else. And PCA in particular specified that the linear projection that's best is the one that retains the most information about the data in the form of variance. So after we project down from d dimensions to k dimensions, we should have preserved as much variance in the data as possible. Okay? You can sort of think about that as like the data being as spread out as possible so that we can still differentiate between all the different data points that we have as best as we can. As it turns out, this d by k matrix that we want for PCA can be computed via an Eigen decomposition of this x transpose x object that we have over here. And we worked out some of the details behind why this checks out mathematically, right? But just as a general overview, we can write x transpose x in the form of some qd q transpose, right? Where d is diagonal, has eigenvalues along the diagonals, in non-increasing order. So they just keep getting smaller as we go down, right? And Q is an orthogonal matrix, and it has eigenvectors in the columns. As it turns out, you can write x transpose x in this way. And then the d by k matrix that we're looking for, the projection, turns out to just be the first k columns of Q. And we're going to write this as Q1 through k. Okay? So we can use this Q1 through k as the d by k matrix that projects our data down from d dimensions down into k dimensions. Okay? This is the high-level overview of what we did last time. So in this way, x here, design matrix, right? N data points, d-dimensional. We hit it with Q1 through k on the right side, right? Q is d by k, so we're going to get n data points, but now k-dimensional. Okay? That's the high-level idea. So that is PCA. And kind of the way that we've described it so far is you can do PCA by sort of computing X transpose X, right? And then doing an eigen decomposition on that in order to find your Q. You know, there are sort of, you know, good software tools that exist for doing this in a fairly efficient way. However, there are limits to this efficiency. So there's actually one more important thing that I want to tell you about, which I mentioned very briefly in like lecture 2 or something like that. But I want to tell you about it in a slightly more detail. And it's called the singular value decomposition, which is an alternative tool that we can use that's very useful for PCA in particular, rather than the eigen decomposition. Why am I telling you about this? It's because of the eigen decomposition of a D by D matrix, the asymptotic runtime is cubic in the sort of dimensionality of your data. Okay, you don't need to know exactly why this is. I mean, that would involve actually knowing what the algorithm is for computing eigen decompositions. We're not going to go over that. Just know that it's sort of not very efficient. Okay. Oftentimes, we actually have a better approach that sort of circumvents having to do eigen decomposition, and it's called the singular value decomposition. The SVD is kind of cool because it's actually valid for any matrix. So we can only do eigen decompositions for like square, symmetric, you know, so on and so forth. Singular value decompositions you can do for any matrix. In particular, we can do it directly on our original matrix X. Okay, so our design matrix, n by d, we can take a singular value decomposition of X into also 3 matrices, which are usually called U, sigma, and V transpose. Okay, so here we have U and V, they're orthogonal matrices, and they contain eigenvectors, but not of X. Okay, U contains eigenvectors of XX transpose, and then V contains eigenvectors of X transpose X. Sigma is also a diagonal matrix, but along the diagonal are what we call singular values, which are basically eigenvalues of X transpose and X transpose X. Turns out they're the same. Okay, so that's what a singular value decomposition is. It decomposes any matrix X into U sigma V transpose, and then it turns out that doing so is slightly more efficient a lot of the times than doing the eigen decomposition naively. Okay, so that's nice, but why am I telling you this? How is this useful? Anyone see something in there that might be useful? Yeah. Kernelization. So we're still looking for just like this linear projection, right? So before we had Q, right? And then we could use Q1 through K, the first K columns of Q, right? In order to do this projection down from D dimensions into K dimensions. We're still trying to do that here, right? But we don't have a Q. So what is it that, yeah. That's getting closer, right? But there's actually a very straightforward answer if you squint at it hard enough. Yes. So yes, that is correct. I mean, we are limiting the number of we're limiting the number of sort of dimensions that we're going into. It's K dimensions. But what I'm still looking for is some kind of D by K matrix, right? Something that goes from D dimensions to K dimensions. Before it was Q 1 through K. What is Q? I got all day. What is Q? Yes. Yeah. Okay, so that is correct, but let me expand on that a little bit. So Q we got from an eigen decomposition of X transpose X. Right? What does that mean? It means it contains the eigenvectors of X transpose X, right? We have the eigenvectors of X transpose X here. They're in V, right? So the important piece here is that V is the same as Q. Okay, so before we did an eigen decomposition on an X transpose X matrix, got a Q from there, and that's the Q that we needed. Now we take X directly, do a singular value decomposition instead, but we still get the matrix that we need. It's just now called V because that's what people typically call it. But I could have easily called it Q here if I wanted to, right? So we can use this V in the exact same way that we used Q before. We just do V1 through K, the first K columns of V, and then that's going to be the matrix that we use to go from D dimensions down into K dimensions. And if this is just doing the same thing, why am I telling you about this? It's because the time complexity is a little bit better. Now it's something along the lines of nd squared plus n squared d, which kind of means, whichever one is smaller, n or d, that term is going to dominate a little bit. Nevertheless, actually this is, typically better than just having d cubed runtime. And we can actually further improve this by only considering kind of the k components that we want rather than computing a full SVD. We can compute something called a truncated SVD, which only gives us the k dimensions that we're actually looking for. Okay, so that is nice, and it's good to know that in practice, this is what people typically do when they want to do PCA. They don't actually do an Eigen decomposition of that matrix. They do an SVD of the original matrix after centering. Okay, so that you always center everything first. Yes? Absolutely, yeah. So that's a great question. So if you have, so I know that X is expressible as U sigma V transpose, right? So what is X transpose X? Well, it's V sigma U transpose and then U sigma V transpose. But U transpose U is identity because it's orthogonal. So then that goes away. Then I get V sigma squared V transpose. So then what? So then you just start equating terms. V is Q, sigma squared is D. Yep. Yes. Great question. So when you, so I'm talking about, centering where you sort of make all the features have mean 0. Do we do anything with the variance of the features is kind of what we're asking here, right? So that actually kind of depends on, your particular domain knowledge and the problem that you're working on. So if you scale the features in a particular way, then you're kind of messing with the variances in your data, right? If you're messing with the variances, then PCA will start giving you different answers, right? Because now the principal components are changing based on how you're scaling these features. So in some cases, you might not want to do that if you, kind of have knowledge that like all of the dimensions are kind of, the scales actually mean something like, oh, everything was measured in like feet per second. So I don't want to actually change these scales. But then if you have different units of measurement, maybe it actually does make sense to do some kind of scaling before you do PCA. Otherwise, your principal components might be kind of biased, so to speak, by the units that you're doing measurements in. So all of these things kind of have some amount of contribution, and it's a little bit tricky to say anything in general without sort of knowing more about the problem. But centering is very important. We always do that. Okay, some more practicalities. How do we choose K? So we're projecting down into some K-dimensional subspace. And we want K to reduce the dimensionality of our D-dimensional data, but how do we actually choose this number? Well, I was thinking about going into the math of this because it's kind of interesting, but there's just too much to cover. So I'm just going to tell you at a high level what it is that you do. If you're curious why the math works out this way, again, happy to chat about it, but it's not something that I'm going to cover in detail. The quantity that we actually typically look at when we're trying to choose K is something called explained variance, okay? So here's what that means. Your original data set in D dimensions had some amount of variance, some amount of total variance, okay? And then when you project down into K dimensions, what PCA is doing is trying to keep as much of that variance as possible, right? But you're projecting down into a subspace, inevitably you're going to lose some amount of variance unless some dimensions in your original D dimensions had 0 variance, which is very unlikely, right? You project down into K dimensions, you're going to lose some amount of variance. How much are you losing? Well, PCA is trying to minimize that, right? But you're going to lose something. So then the question that we can ask is, well, how much of the total variance do we capture in k dimensions when we do PCA versus, the overall amount of variance that we had before in d dimensions. And then as we expand k, we'll capture a larger and larger fraction of the original variance, and oftentimes people choose k just by setting some kind of threshold, like I want to capture 90% of the original variance, and then choosing k in that way. There's actually a very simple formula for calculating explained variance for some number of principal components k. You just look at this D matrix, the D is the, Eigen Decomposition diagonal matrix, and you just look at, what's the sum of the D's that I have up to k divided by the total sum of all the D's. It turns out that these capture variances in this particular eigenbasis, and then so the formula ends up working out very, very simply. And if you do this, you actually get plots that sort of look like this. So here's like an 11-dimensional data set. Okay, so we can go up to 11 dimensions, but we can also consider, only using the first one principal component, or 2 or 3 or 4 or so on and so forth. Here, what this is plotting is each dimension's contribution in terms of how much variance it captures. So you can see that obviously the first principal component is very important, captures over 1/3 of the overall variance. And then as you move down, you start to get diminishing returns, right? So in the number in the bar, right, is how much variance that dimension captures. The number above the bar is the percentage of total variance up to that number of principal components, right? So once you get to like dimensionality 8, you've captured 91% of the variance. That's probably good enough. You could probably actually stop significantly before that and you'd probably be fine. Okay, so this is kind of the idea. You can choose k by looking at this quantity explained variance and then just setting a threshold for how much variance you want to keep around and then choosing k in that way. And sometimes we might do this on a validation set. Sometimes you might do this on a training set, honestly, because there's not really a whole lot of overfitting that you can do here. It's kind of unsupervised learning. Okay, there is another view on PCA that I want to tell you about that I didn't get to last time. And it's a view that we can think of as reconstruction. Okay, so we've talked so far about what does PCA do. PCA keeps around as much of the variance in the data as possible, right? So that's one way that we can formulate the objective that PCA is trying to solve, right? But there's actually another objective that turns out to be equivalent, at least when we have sort of like these linear projections that we're talking about. So another view that we can take on PCA is called reconstruction. Basically, we reduce the dimensionality of x from d dimensions down into k dimensions. And then what we can do is we can attempt to, from that k-dimensional representation, reconstruct what the original d-dimensional x was. Okay? You can't do this perfectly in general, right? You can't do this perfectly because there's more information in a d-dimensional space than there is in a k-dimensional space. But you can sort of ask, at least for my data set, what's the best that I can do in terms of going down into k dimensions and then trying to go back up into d dimensions and figure out what my original data was. So let's talk in a little bit of detail about what does it actually look like to reconstruct x from this reduced representation of x, q, 1 through k. Well, actually, there's a very simple answer when we're looking at sort of these linear projections with sort of these orthogonal matrices. You basically expand back into your original basis by right multiplying by the transpose of q1 through k, okay? So q1 through k is a d by k matrix. q1 through k transpose is a k by d matrix, right? So if I hit an n by k matrix with a k by d matrix, I'm going to get n by d, right? That's sort of like what the original data look like. It's n data points in d dimensionality. You're losing some data here. You're losing some information here because q1 through k transpose by definition can't be full rank, right? So you can't necessarily reconstruct your data perfectly, but it's sort of the best that you can do in this particular case. And remember, these are orthonormal columns that we're dealing with here, right? So q is orthogonal. So if you're using the full q, if k is equal to d, then you'd just be doing x q transpose, which is xi, which is just x. Right, so this sort of checks out in that case. If you're not doing dimensionality reduction, you can reconstruct perfectly, but as you start losing some of the columns of Q, you're going to start losing some of that information that comes along with it. So this is the view of reconstruction. you can do PCA, dimensionality reduction, down into a k-dimensional space, and then attempt to reconstruct what your d-dimensional data was in the beginning. And as it turns out, PCA is the linear projection that minimizes reconstruction error. Okay, so out of all of the possible d by k matrices that I could have picked, call these W, okay, out of all of those possible d by k matrices, it turns out that Q1 through k is the one that minimizes this objective right here. So it's x minus its reconstruction, okay? And then that f is the Frobenius norm, right? It's kind of just like taking your matrix, making it one long vector, and then computing like a 2 norm. So this is the view that sometimes people like to take on PCA. We can talk about, you know, things like variance, preserving variance, but we can also talk about reconstruction and how good you can do reconstruction based on the projection that you use. And so let me go back now, because it might make a little bit more sense. Let me go back to this eigenfaces example, because it's just so fun, you know? And show you one more time that on the left we have sort of original data points, okay, which are actual 32 by 32 images of people's faces. And then in the middle here you have reconstructions, and the reconstructions are done in the way that I just described, okay? So here we're actually projecting down into a 100-dimensional space or something along those lines via the first 100 principal components of data that was originally 1,000 dimensional, right? 1,024 to be specific, right? So here we have projected down into 100 principal components and then expanded back using Q1 through K transpose, right, into our original 1,024 dimensional space. And we can see that the reconstructions are pretty good. It's probably a little bit hard to see, especially if you're in the back. But actually one thing that's going on is that the faces, the big details kind of get captured well, and then the finer grain details of each face are kind of lost, and so you kind of get this blurry effect, although, you know, the reconstructions are still pretty decent. And this is the general effect that you're going to get with something like dimensionality reduction, trying to keep around as much information about the data as possible, but still losing some of maybe the finer detailed things, because those are hard to capture and lower information in general. And let me show you one more time. These are what the principal components look like, right? So there's actually only 36 here. There's 100 in total. But these principal components, they're, you know, like d-dimensional vectors, right? So we can sort of visualize them in the same way that we visualize images. And as it turns out, you get certain things like, you know, that second principal component seems like it's capturing some information about like shading, right? Because it's like light on one side and then dark on the other. And then you get some other things that kind of look like they might be, you know, expressing certain things like the tilt of the face and all these other kinds of things. It's a little bit subjective how exactly you interpret these, but it is kind of interesting that you can sort of form this basis of faces, so to speak, and then capture most of the information about faces in this new basis. Okay. Now we know about as much as you need to know about PCA. Let me tell you a little bit about why PCA is good and why it's bad. PCA is really widely used. Like, it's very, very popular. It's really enjoyed a lot of success in a lot of applications, like if you're just doing data analysis, right? Like you're trying to understand something about this, you know, unlabeled data that you're given, or you're trying to do something like pre-processing for machine learning, right? If you're trying to, you know, use like a nearest neighbor classifier, but what do we say about nearest neighbors? It works better in lower dimensions, right? And nearest neighbor is usually a bad idea in high dimensions. You could try to do something first like dimensionality reduction using PCA before then training your nearest neighbor classifier, right? So these are all things that people have done and people continue to do, and typically it's pretty successful. PCA is a very widely used algorithm, and it's, you know, well motivated, right? Like we actually saw two different motivations that led to the same thing, right? Keeping around as much variance as possible and minimizing reconstruction error. Turns out PCA is motivated by both of those, and it's analytically tractable. We need to, either do an Eigen Decomposition or an SVD, but that's basically it, and that gives us our exact answer. And using the SVD in particular, it can be solved fairly efficiently, even for large matrices, right? But why do we get all of these things? Why is it well motivated from a bunch of different angles? Why is it analytically tractable? Why can it be solved efficiently? It's because it has a very particular restriction, right? And it's that it's restricted to only learning linear dimensionality reduction. So the way that I'm going from D dimensions to K dimensions has to be expressible by some D by K matrix. That's all I get to work with, right? So in the end, we're only going to be able to do linear things. And actually, some of the motivating examples, like that Swiss roll that I showed you on Monday, what we would want to do there is actually some kind of nonlinear dimensionality reduction, right? So here's a related example. It's not exactly a Swiss roll, but it's also nonlinear in the sense that we sort of have this two-dimensional S manifold running through a three-dimensional space. If you do PCA on this, you're not going to get what you want. You can sort of see that the colors kind of start mixing together in particular when we try to do PCA on this data set, right? Whereas what we probably want is to try to somehow unfold that S, right, into its corresponding, two-dimensional manifold. But PCA is not capable of doing this because it restricts itself to only being able to do linear projections. Okay, so this is kind of part of the issue. When you have more and more complex data, PCA is probably going to start running into some issues where it kind of just stops making sense because the assumptions don't really hold anymore for what it's trying to do. So motivated by that, it's also very useful for us to at least briefly discuss some nonlinear methods for dimensionality reduction. Can anyone guess what the first method I'm going to show you is? Just based on sort of historically what we've done in this class. Trying to go from linear to nonlinear. What do you think I'm going to show you? Is it a specific phrase or applying two things together? I guess I'm looking for both. Yes. Kernel Pca, exactly, right? How do we turn linear things nonlinear? Well, actually, kernelization is far from the only way, but it's the way that we're going to start with because it's kind of easy. This is brief because actually, when I say easy, it's not easy at all. Kernel Pca is actually quite involved mathematically. It involves similar tricks that we did before with like SVMs, where we sort of express things as linear combinations of data points and stuff like that. But, at this point, I don't know if that's, the most useful thing that we can be doing with our time is going through more kernel math. So I'm going to tell you that kernel Pca exists, and then we won't really go into detail about it. Yes, we won't go into detail. It turns out that Pca can be kernelized. And we sort of already motivated a little bit why it is that we might want to do this, right? So we're only able to do linear projections with PCA. That might not be a good idea in our original feature representation, for example, like that S in the three-dimensional representation. We can't really do a linear projection down from there into something that we want, right? But maybe, just maybe, depending on the data set, a linear projection could work well in some higher dimensional, more expressive featureization, okay? And if this sounds familiar, that's good. I hope it does sound familiar because it's basically the exact same motivation that we were giving before when we were talking about kernelization for linear models, predictive models, right? Maybe a linear model doesn't do good prediction in the original space, but maybe it could do good prediction in a higher dimensional, more expressive feature space. That was the whole motivation behind kernelization. The motivation is essentially the same here. We just don't have labels anymore, okay? So maybe a linear projection is good in a higher dimensional space, And that's kind of funny if you think about it, right? Because essentially what we're doing now is we're using kernelization to expand the dimensionality and then doing dimensionality reduction to bring it back down. And it seems like that's kind of counterintuitive. Why would you just make it bigger only to make it smaller? It's because they kind of serve actually complementary goals potentially, right? Higher dimensional featureization gives you more expressive features, and then maybe from there, there's a more sensible linear projection that we can do in order to get the lower dimensional representation that we want. So that's kind of the high-level idea behind Kernel Pca. So this is one example. I keep saying things before they show up. This is one example of how dimensionality reduction and dimensionality lifting, like kernelization, don't have to be mutually exclusive. Okay, you can use them together and potentially extract the strengths from both. But there are some downsides, and one downside with something like Kernel Pca, just like with any other kernel method, is that you still have to pick an appropriate kernel. You have to kind of know ahead of time, well, maybe a quadratic kernel will be a good idea here, maybe a Gaussian kernel will be a good idea. You kind of have to think about these things and sort of understand something about your data already, and that might not be particularly easy to do the more complex your data gets. So Kernel Pca could be a good idea if you have a good sense of what kernel you might want to use. Otherwise, some of the more general nonlinear dimensionality reduction things that we're going to talk about next might be a better fit. Yes? Yeah, that's a great question. So the question is, are there sort of tricks in the field for trying to maybe be able to predict, like from the human's perspective, whether or not kernelization would be useful? There might be. I am not totally confident in saying that there aren't, but there aren't really any that I know of that are all that reliable. The first thing is that there's kind of only a couple of different kernels that people use in practice anyway, like polynomial kernels and Gaussian kernels. Like, it's actually quite rare to use anything else. So in that sense, the search space is already reasonably small, so to speak, in the sense that maybe you just are able to try it anyway, regardless of your prior beliefs of whether or not it might work, and then just see what it does is kind of a common tried and true technique that people take on, right? As far as that eigenfaces example goes, it's actually quite interesting that eigenfaces without kernelization does anything, and I think that was actually quite surprising when I saw it, because those images of faces, they're really far from linear, that's for sure, right? But it seems like there still might be some kind of regularity, some kind of structure in that data that allows for generally reasonable things to come out of just a linear projection. But it's definitely not perfect. Like, those images are tiny, and it's still getting pretty blurry results and things like this. And there are sort of, a lot of dimensionality reduction techniques, including the ones that I'll tell you about now, that kind of work better for something like that. So it is totally plausible to me that for something like eigenfaces, the right kernel could make those results better, simply because, based on sort of intuition about that problem, right? Like, in pixel space, images are the furthest thing from linear. So trying to do something linear doesn't seem like a good fit. Therefore, maybe something more expressive like a Gaussian kernel or something like that could help. But is that really based on any kind of rule of thumb? Not really. It's more just an intuition about the problem seems hard, so a kernel could probably help. Yeah. Okay, let's move on and leave PCA behind, and I'll tell you a little bit, again, briefly, about some other techniques that you could take for nonlinear dimensionality reduction that are sort of nonlinear by construction, rather than nonlinear because we kernelized it. Okay? So no more PCA. That's the last of PCA that you'll see in lecture. Let's talk about this idea called autoencoders. This idea is slightly out of place because it probably would be best to talk about autoencoders after I introduce neural networks, which we'll do next week. But it seemed appropriate to put it here because we've already talked about this idea of reconstruction. So hopefully you can still get some of the high-level flavor of what it is that we're trying to do. Okay, so this interpretation, this alternative interpretation that we took on PCA about minimizing reconstruction error, right? It's actually not just an interesting math exercise. It actually does lead to some new inspiration for how we might extend these basic ideas in dimensionality reduction and do things that are nonlinear, okay? In particular, what we're going to do is we're going to think about how Q1 through K we treated as something that we can call an encoder, right? So it's encoding d-dimensional data into K dimensions, and that's the dimensionality reduction, right? And then Q1 through K transpose we can think of as a decoder. It's basically trying to reconstruct the d-dimensional data from the k-dimensional representation that we have. We can replace both of these things, Q1 through K and Q1 through K transpose, with arbitrary nonlinear functions with parameters that we can learn. Okay, so that's the high-level idea. We're going to define some nonlinear function instead of the linear Q that we have, and then use that as our function that goes from d dimensions down to k dimensions, our encoder, and then k dimensions back into d dimensions, our decoder. So let me say that one more time so that people can, sort of try to internalize that. We have an encoder. We're going to give it some parameters that we're going to optimize. Okay, we're going to call those parameters theta like we normally do. It takes in a d-dimensional data point, and it outputs a k-dimensional representation. This is what Q1 through K was doing before. Now we've just made it some other arbitrary function that doesn't necessarily have to be linear and has its own parameters theta that we can do optimization on. Similarly, define a decoder. We're going to also give it some parameters. We're going to call those parameters phi to distinguish them from theta. And this decoder takes a k-dimensional representation and outputs a d-dimensional reconstruction. Okay, so its best attempt at reconstructing what the original data point was. So these things, like I said, we could define them as sort of these nonlinear functions. We haven't really talked all that much about nonlinear functions, but we will in a lot more detail once we start talking about neural networks, which is next week. Yes. So, okay, so here's a general question, right? Does it matter if K is bigger than D? Mathematically, no, but you're not doing dimensionality reduction in that case anymore, right? So in that case, you're doing some kind of dimensionality expansion, which could, for similar reasons as kernelization, might still be useful if you wanted to do that, but it's kind of a slightly different topic, right? Reconstruction is not hard when K is larger than D, right? Reconstruction is really easy because in K dimensions, you could have more information, or you could retain all of the information about your original d-dimensional representation if K is larger than D, right? And then by retaining all that information and going back down into a d-dimensional reconstruction can, at least in a sense, be trivial, right? Because you didn't lose any information, you don't have to really guess about anything. Reconstructions can be perfect. So in the case where we have dimensionality reduction, that's the case where things get hard. That's what people typically think about because they're trying to somehow compress high-dimensional data into some more efficient representation. But you're going to lose information as a result, so you have to think about how do I lose as little information as possible. Yes? Can I repeat why it's nonlinear? I haven't really told you why it's nonlinear. I'm just specifying that we can make them nonlinear if we want. So so this encoder and this decoder, they don't have to just be matrices. They can be some other more complex representation of a function that has parameters that we can learn. But like I said before, it's a little bit out of order because it's a little hard to expand on that without talking more about things like neural networks. But that's kind of the high-level idea. But, I will tell you one more time. Usually in autoencoders, both the encoder and the decoder are neural networks. And we will talk more about this next week. But that's kind of the model of choice when we're talking about these kind of nonlinear functions with parameters that we're trying to learn. Usually when I say that, people think neural networks, and usually you're right. Okay? The reason that I said that the reconstruction view on PCA motivates this is because we can basically use that exact same objective here. Okay, so the encoder and the decoder can share the exact same objective, so they're trying to work together to try to solve the same objective, which is the reconstruction loss that we had before. Okay, so this expression right here, this Frobenius norm that I have, it's basically the same thing that we had before. I just replaced the q's with these respective functions, right? So instead of q1 through k, I replaced that with e theta, the encoder. And instead of q1 through k transpose, I replaced that with d phi, the decoder, okay? But basically, it's the exact same thing. We just swapped out what it means to encode and decode from linear functions to these nonlinear functions that we're learning. Yes? Oh yeah, why is it called autoencoding? This term is pretty old. I think it comes from signal processing, actually, but I think the basic idea is the auto means that you're trying to do decoding from your own encoding representation. There's also, I think there's a thing called auto decoding, which is kind of like representation to data to representation. But, you know, like people typically are thinking about data to representation to data. And having that last step is why we add the term auto. Because if you were just doing encoding, maybe you don't care about the reconstruction part. Maybe you care about something else. You'll also notice, if you care, that there's kind of a slight abuse of the notation here where, you know, I said that, you know, these E's and D's, they take in data points and like a single data point and output like a single representation, or vice versa. Here I've written it as like matrix form, like it's taking in a batch of data or something like that. Please forgive me. You know, we can sort of just, you know, pretend that didn't happen. And the way that we actually do this optimization normally is sort of the way that we were talking about, kind of like optimization for logistic regression, for example. Gradient-based optimization like gradient descent or some stochastic variation thereof. And trust me, you'll see a lot more of this next week when we start talking about how people do optimization for neural networks. There are many flavors of autoencoders. Essentially, people taking the same thing and sort of defining different objectives or maybe slight architectural changes, things like this. There are things like denoising autoencoders, something very popular recently called, or very popular in the last, like, I don't know, 8 years or so, called Variational Autoencoders, VAEs. That's something that's covered in the deep learning class CS182 if you're interested. These flavors of autoencoders are out of scope of this class. We're not going to talk in a lot of detail about these things. And then as a last general note that I'd like to add, next week when we start talking about neural networks, I will also tell you how people can use neural networks for dimensionality reduction without this explicit reconstruction loss. So in that case, we can think of it as doing something more like encoding rather than autoencoding, okay? And as it turns out, neural networks learn lower dimensional representations that are oftentimes very, very useful for a wide variety of things, even if we don't try to explicitly do something like reconstruct the original data point from that representation. And that's a topic that we'll get into in a lot more detail. Okay, one more thing. And this is a completely different idea called neighbor embedding methods. Okay, another way that we can do dimensionality reduction in a nonlinear way, and it's sort of nonlinear by design. Very briefly. So the high-level idea behind neighbor embedding methods is that you have some idea that there's structure in your high-dimensional space. It's just complicated. Okay, the structure in your high-dimensional space is complicated, but it does exist, and a structure is sort of defined by sort of what data points are close to what other data points. Okay, so what you want to do when going from high dimensions to low dimensions using this motivation is try to keep the data points that are close to each other in the high dimensional space also close in the low dimensional space. That's what your objective is going to try to force. Okay, so this is the basic idea behind neighbor embedding methods. You have neighbors in your high dimensional space. Do an embedding such that those neighbors are more or less preserved in the low dimensional space. There is a very popular tool for doing this kind of neighbor embedding. It's called T-distributed stochastic neighbor embedding, or TSNE. Show of hands, how many of you have heard of TSNE? Yeah, it is that popular. So TSNE is a very popular tool for doing this particular type of dimensionality reduction. It has some pretty significant benefits. Like empirically, it works quite well at generating very pretty plots. I'll let you in on a little secret. Over the course of grad school, I used TSNE quite a bit. Never really knew how it worked. I just knew that I could call a function and then take my 100-dimensional data and turn it into 2 dimensions, and then visualize that in a plot. The 2-dimensional data usually looked pretty good. So we're not even going to get into the details exactly of how TSNE works, but the high-level intuition is that you're doing this kind of neighbor-preserving embedding, right? So neighbors that you had in your high-dimensional space, you're also going to have in your low-dimensional space. Doing this nonlinear embedding actually turns out to work pretty darn well for a lot of things, which is why TSNE is very popular. In particular, this this S-shaped 2-dimensional manifold in 3-dimensional space, it's actually pretty well captured by these kind of neighbor embedding methods. So this is actually a slightly different neighbor embedding method called isomap. The details are not important, but TSNE can pretty much do the exact same thing when trying to visualize this data. One important point, TSNE is really good for data visualization. So if I want to take a large data set, or something that my machine learning model has produced, and then compress it down into like 2 dimensions or maybe 3 dimensions, right? And then do a visualization from there, right? TSNE is really useful for that. People typically do not use TSNE for other things like pre-processing your data for machine learning or using it as a general embedding method. The reason for that is that TSNE is something that runs on an entire data set and then generates for you all of the embeddings of that data set. You can't then add a new data point and only embed that data point into this 2-dimensional space that you've learned. You could do that with PCA, right? Because PCA, you just have a queue, right? And you just feed that new data point through the queue to get your new representation. You can't do this with TSNE, okay? With TSNE, you'd have to add that data point and then recompute the representation for all of the data that you have, which can be very computationally expensive, especially if you're getting new data all the time. So typically people, when they think about TSNE, they're thinking about it from the perspective of, I want to visualize some kind of data set or something like that, rather than using it as a general embedding method. And that's it. That's all I have to tell you. So that's dimensionality reduction. Again, if you want any details for any of these things or more resources, just come talk to me. Happy to provide that. But yeah, we actually ended a minute early today. So go enjoy the rest of your day. Thank you.